So I will present you the result we have obtained in team Likable GE. So how we have obtained those results. We are two members, you know that. Myself and David, both professor at École nationale d'aviation civile. The idea was to predict the aircraft takeoff weight, and we want to do that using flight data and trajectory data. So the flight data were the CSV files. We have flight plan data, and we have also flight duration, taxi out time, and front distance. In addition to flight data, we have trajectory data, which are basically ADSB packet file from OpenSky Network. This contains the classical ADSB variables plus the temperature and the wind, which has been added by Junzi, I guess. The takeoff weight, so we have a model that predicts the takeoff weight using features. So we have grouped features in the three groups. So the model here is obtained using Likable library, which is an efficient gradient boosted trees library. So the model is basically 50,000 trees summed together. To select the size of these trees and the regularization parameters, we have performed a random search. So this is for the model part. And now let's have a look at the input variables. So we have at the end nearly we have 600 input variables extracted from different sources. So here we have grouped this 600 into three groups according their sources. So the first group is the flight information that comes from the CSV files. So we have all the variables in the CSV file will be used as input variables, all but the call sign, which is a categorical variable with a lot of categorical value, and we found that it was hurting the predictive performance in our experiments. We have also added the variables, so local time of departure and arrival, great circle distance. The second group is weather at airport, which is basically meters. Using these meters, we have added temperature and wind at departure and arrival airport, and also thunderstorm and fog at the arrival airport. So this was the easy part. Now the most challenging part was to deal with ADSB trajectory. So the first step in dealing with this kind of trajectories is to filter them, and we also smoothed them. Next, we have done some features engineering, so extracting features from the sequence of points. So the first one is the wind along the trajectory, which is basically the wind projected on the ground speed, and you take the average, and it gives a sense if the wind is helping your flight going to where he wants to go or not. Then we extract features from the climb phase. So we have classical features like the rate of climb, the true speed, and so on. And we have two special features. So the first special feature is the energy rate here, which is the variation of energy. The energy here is actually an energy by kilogram. So here we have the potential energy plus the kinematic energy. Kinetic. And this is really related to the mass of the aircraft, because the heavier the aircraft is, the slower it will climb, the slower it will accelerate. Okay. So the second features special feature is mass estimation, an estimated mass, using this physical equation. So what is missing is the thrust and the drag, but it's not actually missing thanks to the OpenAP physical model from Junzi. And using this equation, it's really simple to extract the mass. You just have to find the roots of a second-degree polynomial. Okay, so we have our special features for the climb phase. And the last thing we wanted to extract is the flight profile. And to do that, we want especially to extract features that are really correlated with the mass, so the cruise altitude and the speed, the cruise speed. So let's dive deeper into the flight profile. So here we have plotted 5 flights. We have the altitude here and the time from departure. So looking at this, one might think that it can build a feature, for instance, taking the altitude at a given time, and it will build a feature. It is actually a bad idea because value of these features will represent different concepts from one flight to another. For instance, if we go here and we compute the altitude for 5 flights here, well, it will be this feature will represent the cruise altitude for the red and the green one, the cruise altitude at the beginning of the flight for the red and the green one. It will represent the cruise altitude mid-flight for the orange one, and it will represent some random altitude during the descent for the blue one. So the problem is that different flights have different flight duration. So one way to mitigate this issue is simply by dividing the time by the flight duration. So once we have done this, we can split these flight profiles into 20 slices. And then using these slices, we will compute features. So in each slice, we compute statistics on the point in the slice. So cardinal slice is the number of points inside the slice. We compute also as a feature the median Mach value, the median altitude. And this one is the altitude of the last point in the slice minus the altitude of the first point in the slice. So this feature is designed to detect if we are in climb, cruise, or descent. So, for instance, okay. So at the end, we have this process here will generate one feature, so the flight duration, plus 4 features times 20 scaled slices. So at the end, we have 81 features for this process here. So the other process that is really useful, so the features that are really useful comes from the flight phase. So it's easier here. You just have to keep only points that are in climbing phase, that have a rate of climb superior to 500 feet per minute. Then you put slices, and you do statistics of points inside these slices. So you have the number of points. You have the differences between the actual temperature and the temperature in the ISA atmosphere model. You have the trail speed, you have the rate of climb, and here you have a feature designed to detect if we are in a constant rate of climb. Then we have a statistic on the mass, estimated mass, statistics on the energy rates, And here we have two features designed to detect if point synthesizes are in the initial climb or are in a climb that is simply a flight level change during cruise. Okay, so this generates a lot of features, this product of features. And with all these features, we have good RMSE, but you can obtain more for free just by training the same model, the exact same model with just different random seeds, and then averaging their predictions. Okay, so now the competition is finished, so we can take a step back and see what features make it work. So to do that, I've done some ablation study. So here we have, on the bottom line, we have trained the model with all the features. So we have we have the score we had in the previous slide. And here we have the model, the same model, trained only with flight information variable. And we have this score. Okay, so now we will add the variables here one by one and see which one improves really the model. So thunderstorm and fog variables, it does not improve the model, so this might not be that useful. Cruise, it improves, but not that much. So general climb variable, so just the rate of climb, true speed, so no mass, no energy rate. It's a good score. Mass estimates, yeah, it's good. And energy rate variables, it's really good. It's almost the same score with all the variables. So in conclusion, we have obtained a really good accuracy. So what worked? Well, the information extracted from the climb phase, especially the energy rate. And there are also some ingredients in the recipe, because if you took variables, so you took all the variables minus the special ones, you get also a good score. So maybe there are some things that we are doing right. Maybe the filtering and smoothing, maybe the slices thing. I don't know yet. So in the solutions, some features were not so useful. Thunder and fog at arrival airport and the cruise features. So one question that may arise is that it is possible to extract more information from cruise and the descent phases. We did not extract the information from the descent phases at all. So maybe there's room for improvement. And I hope, so ATM research needs benchmarks that are actually used by a researcher. And I hope that this competition give enough momentum to make this a benchmark that is actually used. And lastly, thanks for the organizers to have put work for this challenge. It has really been fun. I don't know.
Should I?
Yeah, thank you so much for this presentation. It's really insightful. I just want to ask a question with my traffic library hat. And from a usability perspective, I think it would be nice to have the simplest yet good model, because let's say, like, if you want to include the thunderstorm and fog information, that's a pain to get when you. If I want to do my flight dot takeoff weight method, then I don't want to include those crazy features. So maybe it would be nice to have maybe some model that is not as good as the best one you have, but at least with information that you can get for free.
I think it can be done. You have to integrate the pre-process I've done.
I know where you work.
Yeah, I know.
I don't know if you can answer it. I was more interested in what was the weather data that was used on cruise. From which model it was taken?
I don't know actually.
It's easy and
Okay.
So thank you. It's a very clever solution. Have you seen any discrepancies between airlines? Because I know that some airlines have very different climb speed schedule. So I was wondering whether it has impacted the results or not.
I didn't look at that at all. The airline is a categorical variable that we take as inputs. I hope. I didn't look at that. Maybe there's discrepancy. I hope the model takes it into account, but I don't know.